Hello, thanks for joining. I'm going to be talking to you today about the OpenPOWER Open ISA, which is new as of last year. We've contributed, that is, IBM has contributed the ISA to the OpenPOWER Foundation, and it's now being managed there. And I'll take you first through a little bit of history, about power, give you some background, and then we'll talk about the compliancy subsets that allow you to make a compliant hardware design, compliant with the power architecture, royalty-free, and able to do that in a very open way. And then we'll talk a little bit after that about some of the optional features and other characteristics of the Open ISA, followed by a quick discussion of some of the latest additions to the Power ISA in the 3.1 architecture. So first of all, the Power ISA was announced last year in August as being contributed to the open community. So we are very excited about that and looking forward to all the collaboration that happens around open hardware architectures, as well as evolving the power architecture as we move forward and face new challenges in computing and find ways to do it together as an open community. We've actually also put out with that openness, we have a set of guidelines, a set of rules. Those are out there as an end user license agreement. And of course, the basic nature of this is that you get all the architecture rights and abilities to make a compliant design royalty-free. And that's part of the objective here, is to make this architecture accessible to everyone. And at the same time, it's very important that when we do that, we do it in a very compliant way to make it so that the benefits of the cohesive power architecture today last for many more generations to come. So today I'll take you through that a little bit. And how did we define those compliancy subsets? Well, they're actually in a new preface. They're spelled out in a very detailed manner. I'll be going through things at a very high level, but I encourage you to follow up by actually looking at the latest version of the architecture and the preface that actually describes the compliancy in more detail, so that you can answer any of your detailed questions there. I'll encourage you also that at the end of this talk, if you want to continue to chat, find me on Slack, in the Slack channel. And if you have questions that accumulate during the talk, please post them in the Q&A tab on Zoom, and I'll try to answer them at the end, time allowing. So then just in this recent May, we were excited to add the 3.1 version of the architecture. This is the version that's in our Power 10 processor. For those that were listening to the previous presentation, Bill Starkey and I presented on Power 10 and some of its capabilities. It's IBM's server class processor, and it is got a lot of great capabilities, and a number of those come and are embedded right there in that 3.1 architecture. So very excited about that. Also, I'll point out that the Power ISA work group was chartered, and work has begun there as part of the OpenPOWER Foundation, which is run with the Linux Foundation. So very excited to see how that matures. Looking forward to a lot of vibrant dialogue moving forward around power. So as I promised, let's start with a little bit of history here. We'll look back at power. Now, key here is that power already has a very vibrant ecosystem. You can find source code and power support in many open source projects from over the years. And power has a very rich legacy. For those not aware, power actually started with researcher John Cock and his team back in the 1970s. They were actually exploring a RISC architecture. They really wanted to change things up. They thought there was a lot of value in having instructions focused around the most common, the most basic, the most important functions, and be able to do pipelining and other capabilities like that. And they actually developed a RISC prototype, the first RISC prototype in the mid 70s. And of course, then moving to productization, IBM looked at productizing RISC products, and there were also efforts underway at Berkeley and Stanford around RISC, around 1980. And eventually what that turned into for IBM was in 1985, focusing on the upper right there, was the America project. And IBM began to make products around this RISC architecture that John Cock and his team had come up with. And by 1990, that was the beginning of power, performance optimized architecture with enhanced RISC. That's what the acronym stands for. And so the power story really began there. And taking you through that lineage there depicted on the right side, very shortly after IBM first launched its power server line, IBM, Apple, and Motorola formed the AIM Alliance, and they actually began working on the PowerPC architecture, which was the platform used in the Macintosh in the early 1990s. And PowerPC went through several generations there. And actually, in parallel, the server architecture continued on the IBM side, and those actually reconverged into a 64-bit architecture around 1998. And then around the same time, the architecture also was spun off into an embedded portion of its lineage. And so that embedded portion of its lineage began to take form, and you find many IBM Power embedded processors really all over the world, Power in many forms all over the world, and of course even in other planets, right? So we've got Mars rovers up there, we've got space, other space elements up there running Power processors, and Power processors can be found all across the world, everything from automotives to supercomputers. So very rich legacy there, and if you look at that lineage, what we ultimately did is back in thereabouts the early 2000s, the goal was, well, let's try to get those converged back together under one umbrella to really manage the architecture. So there is an entity called power.org, and an alliance was formed with Motorola, IBM, and many others to bring that Power architecture back under one roof. But it was a closed group at the time. It certainly wasn't an open architecture. And so with that, the embedded features did continue, and at the same time, Power, and the IBM server line continued to build on those characteristics, building in through the early 2000s. And so what that ultimately resulted in is a 2.07 architecture. That officially 2.07b was the last of the embedded architectures. And then now continuing on in recent years, going from 2.07 up to 3. All the way up through to 3.0 with Power 9. And then now this, latest development, which is really now launching this open ISA, will be bringing back in flexibility to make the Power architecture, again, very primed for having a consistent ecosystem and at the same software ecosystem, while at the same time allowing for custom extensions again, allowing for innovation in many different spaces. And so that's the Power ISA lineage that we just wanted to take you through there. And then on the left side, you see some of the highlights here from a Power architecture perspective, really walking down the IBM server lineage view of it. But as that architecture advanced forward, a lot of notable additions over time, right? Starting with the base architecture, as I mentioned, adding 64 bits, adding the SIMD VSX capabilities, over time. And then some of the most recent architecture I'll take you through later actually had some really cool capability called prefixing. So that's really opening up the opcode space for the future, giving even more flexibility. The other thing you see there in the table on the left side is the number of instructions that were added over time. And the nice thing about the compliancy sets we'll talk in a few moments is that you don't have to do all the instructions. There's a lot of flexibility here. So you can do everything from a fairly small set of instructions up to the full robust set of over 1,400 instructions and capabilities that the Power architecture allows. So a great amount of flexibility provided here in this architecture. So moving forward, for those not familiar, just a quick overview of how the architecture itself is organized when you're looking at those documents. It's really organized into 3 books. Book 1 is the user instruction set architecture. These are the architectures that are typically used in a compiled application environment. And so, a typical program would be written exploiting the different load and store capabilities, arithmetic, computational capabilities, and so forth. And then you move on to book 2, and there you're dealing with, specific interactions, whether it's thread interactions or interacting with time or interacting with storage or persistent memories or other features of that nature. A lot of these capabilities tend to be embedded in drivers or in specific libraries, and sometimes often even in an assembly language, but sometimes compiled. So kind of moving through the books here, the 3rd book is really for the controlling layers of software. It's book 3. It's the operating environment architecture that defines how supervisors and hypervisors can address the architecture. Interrupts, memory management, other facilities of that, a debug and so forth are all defined in book 3. So that's how the Power architecture is laid out. Now let's take a look at what compliancy is really all about. So of course, the purpose of compliancy is to make sure that contributions in the software ecosystem are very durable and that we have a nice architecture that doesn't get fragmented, that really allows for compatibility and reuse. And Power has done very well at this historically, and we want to make sure that that continues And to do that, we really had to define what does it mean to be compliant. The whole purpose of being compliant means that you have access to those royalty-free rights to use the architecture. If you make a design that's not compliant, you don't get those rights. And so that's really cementing in, for everyone's benefit, that ability to have a durable architecture. And the compliancy is defined by meeting one of the 4 compliancy subsets. In addition, being able to have a number of optional features and custom features as well. So from a base compliancy perspective, there's 4 sets. The top one, the most robust, is AIX compliancy set. That allows you to run the IBM AIX operating system. Then the Linux compliancy set, really geared towards running a Linux server architecture. So being able to fully run the same architecture, for example, that's running in the Summit and Sierra supercomputers, or that IBM uses today to underpin its enterprise Linux offerings. And then we've got the scalar fixed and floating point subset, as well as the scalar fixed point subset. These are slimmer subsets of the architecture with many less instructions required that allow for making simpler designs or even advanced designs, but without taking on all of those features needed to support those more server class architectures. It doesn't mean you can't support Linux. There are versions of Linux that can be compatible here, just not the server class Linux supported by the LCS subset. And then, of course, for all of these classes of compliance, you have a number of optional features. So the architecture contains a number of features that are always optional and can always be added. An important point here is that when you add a feature, it really has to be supported in its entirety. So if a feature is made up of a set of registers and a set of instructions, for example, you can't pick and choose, I want a couple of the registers and a couple of the instructions. If you did that, it would actually make a design non-compliant. That's very important because as we're managing features, features get managed in the ecosystem. And if a feature is enabled, it needs to be fully enabled. And if it's not enabled, then it needs to be not there. So that really promotes binary compatibility. In addition to these optional features that are already part of the architecture, one of the recent changes we made was to define a set of custom extensions, really an architecture sandbox. And I'll go through that a bit later, giving flexibility so that when you're making a design, a proprietary design, and you need to do some special things, maybe talk to an accelerator that's very specific to your machine, maybe adding some other hooks just to hold glue your machine together the right way, that's allowed, right? We've carved out some fairly robust set of architecture to be available for you to do that. And then, the other thing that is allowed here is leveraging firmware in addition to hardware. There are some rules on this. There's a set of things that can't be done or emulated with firmware, but in general, it is allowed to use firmware plus hardware to accomplish architectural compatibility. Okay, so that was a little bit of the basics about compliance. Now let's take another look at this compliancy subset, here shown as a pyramid. And at the top of the pyramid is really the base. It's the foundation. It's the minimum set that you need to be compliant, which actually is that scalar fixed point subset. The scalar fixed point subset ultimately makes up the foundational layer of the architecture from a compliancy perspective. And there's 129 instructions supported to get there. And then if you look at the bottom of the pyramid, that's the foundation of the entire architecture. So that's all the features, including all the optional features. And you can see that that's 1,419 instructions. And this is referencing the 3.1 ISA for the instruction counts. And then you've got, of course, the options in between that we just talked through, right? And you can see that moving down from the scalar fixed point, adding the floating point capability, adds another, 90 some odd instructions. And then the Linux subset adds many hundreds more instructions and other capabilities. And then the AIX, rounding out with yet another set of instructions and capabilities required. And so you can actually choose to be compliant at any of these tiers. And let's say that I chose to be compliant with the scalar fixed and floating point subset, they're shown in yellow. I could always choose other optional features that were added in at lower levels of the pyramid. In other words, as long as I grab a feature in its entirety, I can implement and be compliant with that SFFS subset and then pull in additional features from below. I don't have to pull in an entire compliancy subset, but I do have to pull in features in their entirety. So that's a lot of flexibility, right? You have the flexibility to have only a couple hundred instructions all the way up to, over 1,000 instructions. It's important to understand what these are all about. And of course, the architecture itself is the best reference, but I'll try to take you through a little bit of it just to give a good idea of what's really happening at each of these layers of compliancy. So this is the pyramid inverted that we're showing here. So at the bottom of the now at the what used to be the top of the pyramid shown here at the bottom, and that's the foundation of the architecture, as I mentioned. That's the scalar fixed point subset, 129 instructions, a lot of fixed float or no float, fixed point, ALU, loads and stores. Then we're moving up and picking up the floating point instructions there in the next box in the fixed and float subset. And then we move up from there. And when we get to the Linux server subset, we've now got SIMD, including both flavors of SIMD, VMX and VSX, 64, 128-bit registers come along for the ride with that, along with the requirement to support 64-bit mode, little endian mode, logical partitions, as well as a handful of ops that weren't required at lower sets, involving the overflow bit in the XER register, and then the full nested radix translation. So that allows for, again, that robust server architecture, that enterprise class architecture of Linux. And then moving up one, AIX picks up a number of other capabilities that are required, relating to interrupts, relating to certain operations like atomic memory ops, also supporting big endian mode. Okay, so supporting big endian in addition to supporting little endian. Number of other capabilities like the branch history buffer, event-based branch for debug, compatibility register, broadcast TLBIE instructions, which are critical for an SMP multi-core environment, control register, a number of other floating point classes like quad precision and decimal float, as well as some instructions that are actually deprecated from the architecture in the long run, but required for AIX, which is the load store multiple and the load store string. Finally, SMT capability, so simultaneous multi-threading. So that's the set that's needed there to get to AIX, and also kind of listing then what are ultimately optional features that can be picked up at lower levels. So if you wanted to, for example, as I mentioned earlier, implement the scalar fixed and floating point subset, but you wanted to pick up support for big endian, you can certainly do that. You can pick up support for, branch history buffer or events-based branch, any of those debug capabilities. That's the kind of flexibility you have here to pick and choose discrete features and then bring them in to complement your compliancy subset. And then there's the always optional features, and those are shown there in the white box at the top. Copy paste for accelerators, secure memory facility, data streaming prefetch. You have to implement always the control register, but not necessarily the capabilities. Non-coherent memory with M equals 0, write through memory required memory with W equals 1. Those are so-called WIMG bits, and then power management capabilities as well. And then matrix math assist, which I'll talk a little bit later, is a new set of capabilities introduced in the ISO 3.1. So those are always optional at any layer, can pick those capabilities up, one or the other. So that really describes the set of basic compliancy layers and all those features that you have to pick and choose from and how they've been kind of modularized here. And then you've got a set of sandbox capabilities. So here we're really looking at the fact that in the architecture sandbox, you've got customization that's allowed. And that customization that I mentioned earlier can be very important when you're building a proprietary machine. You want to have some capability that you're building into your SoC or into your system. Maybe you need a unique interrupt vector, that's there. Unique opcode is available for you, SPRs, and then some of the key control registers each have bits defined, whether it's the fixed point or floating point control registers. Those all capabilities are all reserved for this architectural sandbox, this one-off sandbox. So while that's all very important, these custom extensions give you a lot of this flexibility, and we want that, right? We want that flexibility. If you see any limitations, you don't see that there's enough, this is the perfect kind of thing to bring to the working group. But it's also very important that we don't put, in the long run, things into custom extensions that really want to be part of the broader architecture. So if something really belongs in the broader architecture, the path forward is for developers are encouraged to bring those forward and submit a proposal for adoption. And then the adopted proposals will become part of the broader architecture. You don't really want to tie up those proprietary extensions with something that has broad applicability, and that's really for everyone's benefit. You want to put it in, let it become part of the base architecture, let it become a part of the broader ecosystem of support. At the same time, if you do things that are in that custom part, you're not going to get in general as much tool chain support because, there's not as much focus from the broader community there. They're really things that will have to be supported by you since they're custom. And then quickly, I wanted to highlight some of those capabilities of the 3.1 architecture. For those that were in a previous discussion around Power 10, you might have seen some of these, so I won't go into too much detail, but really a host of new instructions rounding up, more of this SIMD versus scalar symmetry, plus adding new capabilities there for 128-bit binary, and a number of other new hooks and capabilities as well, especially around SIMD, where we've added 32-byte loads and stores, loading into and storing from pairs of VSX registers, bit manipulation, and a host of other capabilities here, in the architecture. And then as well, new translation management extensions, copy paste, and I'll highlight at the bottom there the instruction prefix support. So I'll say a few more words about that. Instruction prefix is really about the future for the architecture. It's about opening up the opcode space, but in a very risk-friendly way. So we did it so that you're really moving from a 4-byte instruction. You're also allowing for 8-byte instructions, but always with primary opcode equals 1 for that first 4 bytes. And then a very limited set of capabilities defined presently in the 3.1 architecture. Those come in 2 flavors, either modifying or 8-byte architecture. The modifying form allows you to take an existing instruction in the suffix and modify its capability. And the best example there is we added PC relative addressing for loads and stores into the 3.1 architecture. So you can take existing load and store instruction by putting a prefix in front. You have a long 34-bit displacement, and you can be PC relative. The other flavor is 8-byte opcodes. And so this means a whole new rich opcode space for growth in the future and capabilities moving forward. And so this allows for, as we look at, the needs and demands of new capabilities, like whether it's masking or whether it's a predication or other capabilities of this nature, the prefix provides a great foundation for doing that. In fact, for that optional MMA facility, which is matrix multiply, the matrix multiply accumulate instructions that are in there, those actually allow for lane masking in the prefix. So the prefix itself can specify the masking, to give you an idea. And to give you a little more idea, this opcode space here is shown tons of space open for the future. So kind of focusing on the bottom there, this is the opcode space that's defined in the prefix, entire ranges of bits available, lots of growth, lots of flexibility for the long run, and really making, giving us that leg for the durable long duration of this power architecture and the flexibility we need to tackle future challenges. So that's really what I had to present today. I hope you found it informative. I'll take a glance at the Q&A, see if anything has come in. And if not, I thank you very much for listening today. I think we're also right about at the time. Anyone have any questions? Please feel free to follow up on Slack, in the Slack channel, and I'll be happy to answer them.